Okay, welcome, peeps. There we go. There's me. I see me. Okay, cool. Welcome to Cal 1, 3.3, derivatives of logarithms and exponentials. Oh my goodness, stuck in quarantine. What else? What do? You do math. Okay. So again, here's the OneNote. Remember, you can download the Word file and the PDF on the OneNote. Okay, so this is our last lesson before your exam. So this is derivatives of logs and exponential functions. So first thing we get into is the derivative of a common log function. So if you're given f of x equals log base a of x, then the derivative is given as 1 over x times the natural log of a. So whatever the base is here becomes the value inside the natural log of the derivative. So log base a of x of 1 over x times the natural log of a. Okay, cool. All right, and now the chain rule derivative. If you have log base a of g of x, the chain rule derivative says that this equals 1 over g of x times the natural log of a. So you see that this g of x goes here, this base goes there, and then the derivative of g of x, whatever function's on the inside, goes out here. Okay. Another way we could rewrite this is just as g prime of x, gross. Oh, didn't do all that, whatever. G prime of x over g of x times the natural log of a. Yeah, it's natural log, whatever. Okay. So that's if you're doing the derivative of a common log function with chain rule as well. Now the easy one here is the derivative of the natural log of x. The derivative of the natural log of x, 1 over x. That's easy. So much better than the one above. Okay. And then the chain rule derivative for the natural log of x, the natural log of g of x becomes the derivative of the inside function over the inside function. So it's just g prime of x over g of x. That's it. Or I could also write it as the natural log. Well, before I do that, I said d over dx of the natural log. Oh, cooperate. Come on. I know it's been a long day. Of the natural log of u could also be considered u prime over u. Same thing, just not, there's no g of x, just replace it with u. So whatever is easier to look at. Okay. Same with the one above. You can make them u primes if you want it. All right. With that being said, let's go ahead and practice our derivatives. And for the very first one, we're going to be doing the chain rule derivative for log base 10 of 2 plus the sine of x. So our derivative is going to be f prime of x equal to the derivative of the inside, which would just be the cosine of x, over the inside function 2 plus the sine of x times the natural log of base, well, not of base 10, just of 10. And that's it. This is the derivative of the inside. And then this part is the inside function. And this was the base of the log. Now it's no longer a base it becomes the value inside the natural log. So that's everything that happened. So the chain rule derivative for the common log is going to be the derivative of the inside function, which was 2 plus the sine of x. The derivative of that is just cosine x, over the original inside function times the natural log of the base of what originally was the base of 10. So the natural log of 10. There it is. That's using everything above, right there. Okay. Now, we'll use the chain rule derivative for natural logs on this one. And this one is quite easy. So this one, f prime of x. So by the chain rule derivative, this is going to be the derivative of the inside, just 3x squared over the inside, x cubed plus 1. That's it. And again, that's the derivative of the inside. And that is the inside function. It's as easy as it gets, y'all. Okay. Before moving on, I'm going to write some log properties that we need before going. No, I'll write them on the next page. That's fine, because we'll use them on the next page if we have to. So before moving on, let's label this as log properties. Log props, how's that? Okay, so 3 main log properties that can make your derivatives so much easier if you remember them. The 3 main ones. This one first, log or natural log. I'd say natural log. Let's say natural log of x times y gives me natural log x plus natural log y. Natural log of x over y gives me natural log x minus natural log y. And then the last one, natural log x to the n is n times the natural log of x. These are log properties that you should know already. Not corona yet. Okay, so these are properties that we should know already. Okay. So here we go. So these are log properties. These are algebraic properties. Have nothing to do with calculus, but can make the calculus easier. So again, stuff we should know. So number 3, derivative of the natural log of sine x. Again, chain rule derivative of the natural log function. So this will just become the derivative of the inside, so the derivative of sine, cosine x, over the original inside function of sine x. That's it. But now let me ask you, what's cosine over sine's identity? Cotangent, that's right. Good job, guys. There you go. Do we have to do this? Yes, do it. Am I going insane? Yes. Okay. Now, f of x equals the square root of the natural log of x. Before we take the derivative, of course, you need to rewrite the radical. This becomes parentheses natural log x raised to the 1/2. Okay. Now we're ready for the derivative. So we get f prime of x equals 1/2 natural log x to the negative 1/2. This is chain rule, so that's the derivative of the outside times the derivative of the inside. What's the derivative of the natural log of x? 1/x. Okay. All right, so now cleanup time. All right. There we go. Hopefully you can't hear the fan over all that. Sorry. It's hot up here though, but I'm willing to sweat for a bit. Okay. Cleanup time just becomes (1 over 2x square root natural log x). Done. Okay. I mean, the little step that I didn't put was first it could become 1 over 2x. Oh my goodness. 1 over 2x natural log x to the positive 1/2, which then brings us there. Okay. Now, number 5. Oh my goodness. Sorry. I think because of the fan blowing straight up my nose. Okay. Okay. So on this one, well, you notice that all of this is inside the natural log. So we could, well, will have to be chain ruled, but it's also going to be a chain rule with a quotient rule. Now that seems like it would make life really terrible. That's why I said, remember your log properties. So we can avoid quotient rule altogether if we use our log properties. If we use log properties, which means that if we do that, you can actually expand this to d over dx, put a bracket to be neat, the natural log of x plus 1 minus the natural log of x minus 2 to the 1/2, close bracket. And all we're doing right now is expanding by log properties. So there was a quotient on the inside, we do quotient and expand it to the difference. And now we have a little more cleanup to do before we take the derivative because of this exponent. So now we are still simplifying by logs. So this becomes d over dx of the natural log of the, get out of here, Technical difficulties today. Of the natural log of x plus 1 minus 1/2 natural log x minus 2. Okay. We are now ready to take the derivative, and on both of these, you will do chain rule. So both of these get chain rule. So what we end up with is, for the first chain rule, is the derivative of the inside. So the derivative of x plus 1 is just 1 over the original inside of x plus 1 minus 1/2 times, again, chain rule. The derivative of x minus 2 is just 1 over the original inside of x minus 2. Okay, now clean it up. 1 over x plus 1 minus 1 over 2 times x minus 2. Done. If you want to combine the fractions, then you know how to do so. Just get the common denominator and put them together. But I'm telling you that the log properties, using them on this, make life a lot easier. It would have been better than doing quotient rule in there. That's why I crossed it out. Okay, let's keep going. Okay, so like I said, logs will make your life easier. Students hate logs. I have no idea why. There's only 3 rules to them that you need to know to make your life easier. They just refuse to learn those 3 rules. Makes no sense at all. Okay, so with that being said, we're going to jump into logarithmic differentiation, which means that given an equation that looks very complicated to take the derivative of, we will apply logs to both sides of the equation, simplify it by the laws of logarithms, by the properties of logarithms, and then take the derivative. There will only be one implicit derivative that we have to do, and that will happen on the left side. But I will work through that whole process. You'll see what I'm talking about. So, number 6. Before we even think about using logs, think about what you would have to do to this if you didn't know anything about logarithms. How many derivative rules would you have to apply to this? Well, first off, the whole thing would need quotient rule. Second, the numerator would need product rule. Third, everything in here, the square root and 3x plus 2 plus 5, would need chain rule. So you would have to apply all 3 rules and do a lot of algebra just to get this derivative. Well, I'm telling you now that if we use the properties of logarithms, our life gets a lot easier, which means that we don't really have to worry about quotient rule. We don't really care about product rule. We may still have to use some chain rule, so that's okay. Using one rule out of all 3, that just sounds like a deal. So let's go ahead and see how logs make our life so much better. Okay, so let me erase all of this. You'll see it on the video. Okay, so here we go. I'm going to say I'm going to compose both sides with the natural log. So you get natural log y equal to the the natural log of all of this. And I'm going to put the square root into exponential form. Now, we will expand the right side by log properties. So, in the numerator, that is a product of two terms. So you will expand it by the log property, the product to sum. Okay, so with that being said, we are expanding, and I get natural log of y equal to the natural log of x to the 3/4 plus the natural log of x squared plus 1 to the 1/2. And now what you must realize is that this whole thing is a quotient, so you will subtract the natural log of 3x plus 2 to the 5th. Cool. What's up, dude? Okay, I'm back. So we still have some expanding to do. So we've expanded the numerator by product to sum, and we expanded the whole quotient by quotient to difference. So that's minus the natural log of 3x plus 2 to the 5th. So this is how we've expanded. And now only one more expansion by logs. We must get these powers and bring them down by the power rule for logs. In no way is this a derivative. This is the power rule for logs. We haven't even started any calculus yet. We are just simplifying this algebraically. So no calculus has been used at all. Okay. So natural log y equal to 3/4 natural log x plus 1/2 natural log x squared plus 1 minus 5 natural log natural log 3x plus 2. Okay. Now we are ready for the derivative. Okay? We're ready for the derivative. So what I'm going to do is just say d over dx of the natural log of y and d over dx of everything on the right side. Okay. So the left side of the equation, here comes the implicit part, the only implicit derivative. And when I say implicit, is because it's d over dx of y, which gives us y prime, okay? So, first off, we're doing the chain rule for the natural log of y. So this means that we want the derivative of the inside function with respect to x. Well, the derivative of y with respect to x, the implicit derivative of y with respect to x, is going to be y prime over the original inside term, the original inside function of y. And there it is. That's the implicit part. So this is an implicit chain rule. That's the implicit chain rule, which becomes that. That's the only implicit part on this. That's it. Okay. Now we continue, and we get 3/4 times the derivative of the natural log of x is 1 over x. plus 1/2 times, now this is a chain rule derivative. The natural log of x squared plus 1, we do the derivative of the inside function. So the derivative of x squared plus 1 is going to be just 2x over the original inside function of x squared plus 1 minus 5 times, again, chain rule derivative on this natural log. We want the derivative of the inside function, 3x plus 2, which is going to be 3 over the original inside of 3x plus 2. Now, the derivatives are done. Now it's just cleanup time. So, starting back, y prime over y equal to 3 over 4x plus, if you noticed, this 2 and that 2 cancel. I get x over x squared plus 1 minus that 5 and that 3 multiply, 15 over 3x plus 2. Okay, almost there. Now our job is to solve for y prime. So to get y prime by itself, you have to multiply this y to the right side. So multiply this y to the right side. So that gives us y prime equals y times all of this, 3 over 4x plus x over x squared plus 1 minus 15 over 3x plus 2. Okay, we're almost there. There's one more thing to do, and it's really easy. What is y actually equal to? And that, we go back to the very beginning of the problem. So we look at this y, and we look at this y above. Well, now this y is going to get replaced by all of this. So that's what you're going to plug in for y. X to the 3/4, square root of x squared plus 1 over 3x plus 2 to the 5th, and that's it. We're done. So all of that gets plugged in for y. Okay. So y prime equals, x to the 3/4 times the square root of x squared plus 1 over 3x plus 2 to the 5th times all of that. 3 over 4x plus x over x squared plus 1 minus 15 over 3x plus 2. And that is our final answer. There you go. Now, imagine if you were doing this by product, quotient, and chain. You'd still be going. This could take you 30 minutes to an hour to do by product, chain, and quotient. If you want that life, you choose it. But it's going to let you know now, our answers won't look the same. This is the easiest way to do it. So accept logarithms into your life. In the time of despair and pandemic, logs are your savior. Word to your mother, okay? All right, let's move on. Let's do it again. Number 7. Okay, looks complicated. Apply natural logs to it. Now, does this mean to apply natural logs all the time? Sure, you can do it if you really want to. This is if it looks complicated, sure, apply a natural log and see what happens. So we're going to do this again. Natural log y equals natural log of e to the negative x cosine squared x all over x squared plus x plus 1. Now expand. Natural log y equals natural log e to the negative x plus, now for this cosine squared x, I'm going to rewrite it as cosine x squared. So that's what you're going to see on my next line. Natural log of cosine x squared minus the natural log of x squared plus x plus 1. Okay. I don't think I need those out right now. Okay. So cleanup time. The only thing we can do here, bring down this negative x, bring down this 2. On the last term, there's nothing we can do there. You leave it as it is. Okay. So natural log y equal to negative x natural log of e plus 2 times the natural log of cosine x minus the natural log of x squared plus x plus 1. Okay. All right. We are almost ready for the derivative. Almost. But does anybody know what the natural log of e is? 1. That is correct. So the natural log of e is always going to be 1. Where could I write that at? I'll write that somewhere. The natural log of e is always 1. Again, stuff we should know already. So, back to it, not taking the derivative just yet. You get negative x plus 2 natural log cosine x minus natural log x squared plus x plus 1. We are now ready for the derivative. Okay. All right, so I'm going to say d over dx of that and d over dx of all of that. Left side is implicit again. So moving up, you give y prime over y automatically. And now here we go. Derivative of negative x, negative 1, plus 2 times chain rule derivative on the natural log of cosine x. So the derivative of cosine is negative sine x over the original inside function of cosine x minus chain rule derivative on all of that. the derivative of the inside function, the derivative of x squared plus x plus 1, is 2x plus 1 over the inside function, x squared plus x plus 1. Okay. Now, cleanup time. So remember that this is times, that's 2 times that. And I get y prime over y equal to -1 plus 2, actually no, minus 2, and what is the identity for sine over cosine? Tangent. That is correct. Okay. So you get -2 tangent x minus 2x plus 1 over x squared plus x plus 1 multiply this y to the right side. Okay. And we get y prime equal to y times all of that. -1 times 2 tangent x minus 2x plus 1 over x squared plus x plus 1. And then remember what y was and plug it in. This y is the same as that y. So let's plug it in. E to the -x cosine squared. Okay, coming down for our final answer of y prime equals e to the -x cosine squared x over x squared plus x plus 1 times all of this. -1 minus 2 tangent x minus 2x plus 1 over x squared plus x plus 1 and done. It's ugly, but it's easier to do with logarithms. Okay? All right, logs are your friends. Okay. Again, that looks complicated, so we introduce logs. And maybe a question could be, why aren't we using the common log? Well, the common log would make the derivative a lot harder. So we are using the natural log. It makes it a lot easier, and it's only 2 letters. Just saying. Natural log y equals, oh yeah, before I begin, we can rewrite this as x to the 1/2 raised to the x, which is the same as x to the x over 2. Same thing. So that's what I'm going to roll with. Natural log x to the x over 2, which means that now this becomes natural log y of x over 2 natural log x. Okay, we are now ready for the derivative. So d over dx of this and d over dx of that. But now if you notice, this part here has to be product rule. So f will be x over 2. G will be the natural log of x. F prime is 1/2. G prime is 1 over x. Okay. Now we can move on, meaning that the natural log of y is equal to f prime g 1/2 natural log x plus x over 2 times 1 over x. Ha, what did I not do? I did not do the derivative on the left side. It's okay, easy fix. Fair enough. Implicit derivative on the left side, y prime over y. See how easy that was to fix? Okay, so now clean this up, take the y on the bottom, multiply to the right side, so we get y prime equals y times 1/2 natural log x. If you noticed, these x's cancel, so you would have plus 1/2. Now all you have to do is bring back what y was. So there's y, and y is the square root of x to the x. So y prime equals square root x to the x of 1/2 natural log x plus 1/2. You could even factor out a 1/2. Why not? Y prime equals 1/2 square root x to the x times natural log x plus 1. There we go. Yeah, didn't do too bad writing down. Okay. Stop it. There we go. Okay, so that is logarithmic differentiation. Now, we get into exponents, derivatives of exponentials. Okay, so first is the derivative of the function a to the x. Well, that derivative is still a to the x times the natural log of a. So whatever value the base is, that's the value that's inside the natural log. Okay, and then now you get the chain rule derivative. D over dx of a to the g of x is still a to the g of x times the natural log of that base a times the derivative of the exponent g prime of x. Okay. I don't know how to make that any simpler. It's ugly, but that's it. Now to the easy stuff. The exponential function. The derivative of e to the x. Well, the derivative of e to the x is still e to the x. Wow. The derivative of e to the x is itself e to the x. And now chain rule derivative, if it's e to the g of x, then that derivative is still e to the g of x times the derivative of the exponent, g prime of x. Okay. Okay, let's try them out. So first one, d over dx of 10x, 10 to the x squared. This is going to use the chain rule derivative for the exponential function. All right, so the derivative is just going to be 10 to the x squared times the natural log of that base of 10 times the derivative of the exponent. Well, the derivative of x squared is just 2x. That's it. We can't do anything else. And yeah, there's no way to make it pretty. So if you wanted, you could rewrite it as 2x natural log 10 times 10 to the x squared, but it doesn't matter because that's all we can do. Okay? All right. Okay. All right. Next, same thing. We're going to take the derivative. But before we do, I'm going to rewrite this as 5 to the negative x to the negative 1. So negative 1 over x becomes that. Negative x to the negative 1. And now we'll take the derivative. So y prime equals the same thing, 5 to the negative x to the negative 1 times the natural log of base 5 times the derivative of that exponent, which is positive x to the negative 2. Ugly, ugly, ugly. Nothing you can do about it. We can only rewrite it probably just as y prime equals 5 to the negative x to the negative 1 times the natural log of 5 over x squared. That's good enough. Or maybe even just the natural log of 5 over 5 to the 1 over x times x squared. Either or. Ugly, 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 I know. Okay. Now we do the chain rule derivatives for e to the x. Okay. Well, with that being said, your derivative y prime is going to be e to the tangent x times the derivative of tangent x, which is just secant squared x. That's it. Can't do anything else. Oh my goodness, we reached the last one. Number 12, same thing, derivative of the exponential function, but now it's e to the negative 4x times sine of 5x. So before you do anything, that has to be product rule. Just choose green for that. So f is going to be e to the negative 4x. G is going to be the sine of 5x. F prime, chain rule derivative of e to the negative 4x. You get e to the negative 4x times the derivative of the exponent, which is negative 4. Chain rule on the right side. On g, g prime is going to be cosine 5x times 5. Now we can pretty these up a bit. F prime, negative 4, e to the negative 4x. G prime, 5 cosine 5x. And let's finish our product rule. Okay, so f prime g, so this means that y prime is negative 4 e to the negative 4x sine 5x plus g prime f. Five cosine 5x times e to the negative 4x. Okay. Make it pretty. I see a greatest common factor of e to the negative 4x. And that's probably it. So y prime equals e to the negative 4x times negative 4 sine 5x plus 5 cosine 5x. And done. There it is. That is logarithmic and exponential differentiation. Remember that logs save lives. Okay? Logs save lives. All right. Yeah, I think that's it, guys. I will be sending you these notes shortly. See y'all later.